All right, I want to go over this assignment on our discrete random variables. And this is actually a second time going through the key on this assignment because after having class today with my students, they had some questions and brought up some things. And then, even the number two, I found that I had made a common mistake on it. And so I want to go through that with you. It really ended up being a good thing to point out this very common mistake that gets made that I, in my haste or whatever it was, had made that. Now, I wanted to first talk to you about one thing that was a point of confusion to one other student, and I thought, you know what, I probably should fix that. So on this number one, of course, we've got here the grade points of 4, 3, 2, 1, 0, and those probabilities. So the intent of this, of course, was that it was a discrete scenario because there was a finite number of grades that could happen, the 4, 3, 2, 1, or 0. But what was a point of confusion for one student, and rightfully so, was this right here. So she had thought to herself, oh, if it's grade point average, then grade point average can be something like 4.1 or 4.2 or 3.8 or 3.6 or whatever. So then that would make it continuous. So that is true. So in essence, I was not correct in calling this X random variable a GPA. What it actually is then is so I should, and I'm going to go back and fix this, let X be the grade point in that business statistics. And so I'll define that out later made in the business statistics class. Okay, so the grade point. So it wasn't really the average. So those then now is discrete 4, 3, 2, 1. Also, then wanted, so then here we have this, your context, and you're explaining that greater than or equal to 3. So this is a proportion of those business statistics students who get a B or higher. So context. And then here, do the probability notation of the probability being X is less than 2. And so you could also write it as probability that X is less than or equal to 1 because that was a D or an F, technically. Now, this next one is where I want to first show you what I did wrong. So I'm going to first show you my wrong thought process, which is a common wrong thought process that students make. And of course, I did. And then we're going to talk about how to fix that and what it really should be. Okay, so here is this situation. So hopefully you understood this situation of where this couple is having children until they get a girl. But then even if they've had 3 boys, they're going to stop at 3 children because they're like, okay, 3 is as much as we can do. So my 2A is correct in that here are the possible ways that the couple could have children and follow that little rule they've made up for themselves. So they could, straight out of the bag, have a girl first off. Okay, so that could happen. And if that happened, then you had 1 child. Okay, they could have 2 children because that would happen if they had a boy and then a girl. All right, or they could have 3 children. And the ways that 3 children would happen is if they had a boy and then a boy and then a girl. Okay, or there's another way you could have 3 children. They could have a boy and then a boy and then another boy, because at that point they're still going to say, okay, we've met our limit of 3 children, so we're done. So here is where this is a mistake. I had inadvertently thought, in my haste or whatever it was, I had said to myself, oh, look, there are 4 different ways, situations. There's 4 different situations that can happen. 1, 2, 3, 4. And so, then one of those 4 ways is the way you have 1 child. And one of those 4 ways is how you have 2 children. And 2 of those 4 ways is how you have 3 children. And that is wrong. Huh. Man, that got me. So let's talk about what is correct. What is correct is this. You have to show the probability of that event occurring. So the way that this could happen, it's not 1 out of 4. It's the way that you can first have a girl is 50-50 chance. So you either on the first out you have a boy or a girl. So this probability is actually 1/2 that you will finish with just one child. Okay. And then in order to have 2 children, this had to happen where you had to have a boy and then you had another boy, then you had the girl. So that's 1/2 times 1/2, and that's how you get that 1/4. That's how you're getting that. And then here you got a boy and a boy and a girl. So that's your 1/2 times 1/2 times 1/2 that I show here. Or that's addition. You get a boy, 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 and that's the 1/2 times 1/2 times 1/2. So that's, 1/8 for the 1/2 times 1/2 times 1/2 plus 1/8 for the 1/2 times 1/2 times 1/2, which is the 2/8, which is 1/4. So that is how these probabilities are 1/2, 1/4, and 1/4 for 3 children. Whew. So I messed that one up. And then here you have this, then this is the mean and standard deviation that would come out from that situation. Okay? All right, next. Oh, this is a good one because this is a very simplistic version of what happens with an insurance company, but it kind of gives you an idea of how things work. So, with an insurance company, the policy costs $100. So, I, as a client, I will pay the insurance company $100. But if there is a major injury suffered, then the insurance company will pays out. Usually, they're paying out around $10,000. If there's a minor injury, then they end up paying out about $3,000. Now, then they, actuarial tables and so on would give these probabilities. So here's the probabilities. 1 out of every 2,000 policyholders. So in the long run, 1 out of every 2,000 they have is going to be major. And then 1 out of every 500 is going to be minor. So then the rest of them are going to be, no injuries, okay? They won't have to pay out. They only take in that $100. So create a probability. Remember, we need to know the perspective, the company's profit or the insurance or the person's, the client's profit or what they're paying. So what's the company's profit? So here we go. Here are things that could happen. You either have the major injury or the minor injury or no injury. So there are the discrete 3 possible outcomes. So X is the company's profit. So here's how this works. If a major injury occurs, the insurance company takes in $100, but then has to pay out $10,000. So the insurance company is actually $9,900 out at a loss. If a minor injury occurs, they take in $100 from that client, but they have to pay out $3,000. So the insurance company is actually $2,900 at a loss. And then, but if there's no injury, which is happening to a lot of clients, they take in that $100 and then they don't have to pay out for that person. So here were those probabilities we were told. 1 out of 2,000 for a major injury, 1 out of 500 for a minor injury. So what I did was I added those two together and then subtracted from 1 to figure out this probability. So 99.75% of the clients will have no injury and they will just be banking that $100. So based on this probability distribution, we can then see on average per client, what is this insurance company making on average per client, every client. So here we go. So there's the average, the negative 9,900 times how that happens, the negative 2,900 times how often that happens, and so on. So they are making $89, which doesn't seem like a lot, but $89 on average for every single client. So, do they want more clients? Yes. Are they going to have cool commercials like the Geico ones? I like those, and I like the Liberty Mutual ones now. Those are really kind of funny. So, do they put commercials out there on TV and so on and so forth so that they can have more clients? Yes, absolutely. So, because they know on average, in the long run, they're banking $89 per client. All right, that's how it works. This is a simplistic version, and it's much more complicated because there's really much more variables, hence all the smart mathy people doing that stuff, but that's what's happening. Interpret in words what this means. For every policy holder, the company will make $89 on average. Ooh, you know what I didn't put in there, and I should? I should have put, in the long run. Or, for many, I guess for every policy holder, I think for many, for many policy holders. Okay, I don't want to forget that idea of in the long run. Okay, all right, next. Create this here. So we had two spinners. So here were the spinners, and then these red numbers are the sums that we get. See, 1 and 1 gave a sum of 2, and so on. So those were the sums. So then we make a probability distribution table from this. So the possible outcomes, it's discrete. 2s, 3, 4, 5, and 6. And so how frequently do those happen? 1 out of the 9 versus 2 out of the 9, sum of 3. 3 out of the 9, sum of the 4, and so on. And then from that, you can get your mean and your standard deviation. So you want to make sure that you're showing the proper work, x minus the mean quantity squared times the probability, plus ... If you have the table, then you can just do your sequence with the first and the last in the sequence. All right, and so that's what it comes out to be. So there we go. There is your assignment for your probability or discrete random variable probability distribution tables, and I hope you did well on that.